we see Datapath design of MIPS32. So in which we have seen that how we are actually executing a particular instruction and what are the micro operations that are required to be executed. How the data path is actually designed, we will see here. So in data path design, there are five stages. First is the instruction fetch, second is the instruction decode, third is the execution stage, fourth is the memory access stage, and fifth is the write back stage. So we will see one by one. So first stage is the instruction fetch stage. So in the instruction fetch stage, from a memory PC, we load the content of memory location pointed by PC, and we will fetch the data put into the instruction memory to the IR. At the same time, PC will be incremented by 4 and it will be stored in a NPC. So we will require a 32-bit PC, 32-bit NPC, as well as a 32-bit adder. So we see that the PC will hit the instruction memory. PC contain address of next instruction to be executed. So it will be instruction memory and the data will be available in the IR, and the PC is added with a constant value 4 and this is loaded into NPC. So these two operations can be performed during the instruction fetch stage. So program counter, it points to the address of the next instruction memory. Instruction memory stores the instruction program of the program being executed, and instruction register holds the fetched instruction from the memory. So next stage, instruction decode. So in this instruction decode stage, we decoding the instruction and fetch the particular fields that are registers, source registers, destination registers, and immediate field. So from the register bank, RES, RT, and RD, from IR it is a coming, and the from the register bank A and B it is a going, and the after sign extension it is a going to IMM. So one of the source register value is coming depending on RES, another source register value is coming from RT, and the immediate value which is a sign extended to make a 32-bit if stored in a immediate. So for the calculation of immediate, we use a sign extension for 16-bit immediate, and a immediate one it is a calculated with using a padding 2 zeros to 26-bit immediate field, and the decoding is done in a parallel with the reading the register operand with RES and RT. So our third stage is a execution stage. So we are looking for step by step execution. For the execution, we all know there can be various kinds of operations that are present. Arithmetic operation, jump branch address calculation. So for all these kinds of instruction, we see that a particular data path will be sufficient. So we need to add with the immediate value. So there is a mux which is attached to ALU having two inputs, and this ALU one is coming from NPC, another is coming from A. So depending on the select lines that can be taken care which input will be going. So from memory reference, A will be coming accordingly to the select will get activated and immediate value becoming. So there we can see that A and B are coming from 2 mux, and along with B immediate value can come in here which is available after ALU operation. The ALU output is available in ALU out. So ALU out is available in ALU out. So we are doing this of operation and putting it in ALU out. So we use a 32-bit ALU out. One bit condition is required for the condition checking, and a 32-bit 2:1 mux is also required. C for a resist C for a register ALU operation. So if it is a register, then input will be A should go and a B should go. So for register, A should go and a B should go. In that case, the select line will be selected and A input will be go one input of ALU and B input will go another input of ALU, and the operation will be get performed. Similarly, for register any immediate value, A will be go from one mux and immediate value of going from another mux to the input of the ALU, and the uh, output of ALU it contains in ALU out. And for a branch NPC value must be added with the immediate value. So for branching, first mux is selected from NPC and second mux will be selected immediate value, and in NPC by shifting a, so the NPC value must be added with the immediate value by shifting a it left two positions. So in this case, the mux NPC value will come in, and from this mux, the immediate value will go on. The operation will performed. Similarly for condition, the condition will be available based on A of code 0. So A will be operated with a 0. So input is coming will be checked with 0 and the condition will be outputted here. So all these operations are actually performed in an execute stage using this data part diagram. So fourth stage is a memory access stage. So in this memory stage, all instruction will require a memory load operations. All instruction are required a memory load operation, store operation, branch operation, and all other operations. So NPC is stored in a PC. So NPC is stored in a PC and particular memory stage. So let's us see the data path of memory stage. So what happens? This is a data memory from where we will fetch data. Now we know that if we need to read it from the particular location, we need put addresses in MDR. Put addresses in MDR, and basically then we will hit the data memory. So in this case, ALU out. So in this case, ALU out is a read and it is stored in a LMD. So ALU out is stored in LMD, and ALU out put in the data memory, and then the value will be read can be stored in a LMD. So for the load instruction, this happens where a memory located pointed by ALU out is a read and then stored in a LMD. So similarly for other operation can be instruction, store instruction, in which store instruction PC is loaded with NPC and LMD contain memory content of ALU out. So in a branch condition, if a condition PC is fulfilled, then the output will be stored in ALU out, else PC contains NPC. And for other instruction, PC contains data of NPC. And the branch instruction, so for a branch instruction, the branch instructions update the data the PC depending upon the outcome of the branch condition. So PC is depending on output of the branch condition. So fifth stage is the write back stage. In the write back stage, we write the values into registers. So finally, whatever value, either the value is coming from ALU out or the value is coming from the memory, it should be written back into the register. So in some cases, RD is a destination register and some cases RT is a destination register. So example for in R type instruction, the destination register is the RD. In I type instruction, destination register is the RD. And in a load load word instruction, RT is a destination register. So accordingly for register operation, this ALU output stored in RD. For a register immediate ALU operation, ALU out stored in RD. And for a load instruction, the LMD is stored in RT. And so in this, how it can be done, and it can be selected from MUX, either LMD or ALU out. So till now we have seen the various data part that is required, the various stages in IF, ID, X, execution, memory, MEM, and write back. So in 5 stages we can see that what is the data part is required in a MIPS. So let us putting it all together. So where we have discussed starting from instruction phase to ID, then execution, then memory, and finally to write back. So this overall picture gives an idea how it is actually happening. This is a data part that is there for a MIPS. So here initially the initially PC hits the instruction memory, and the instruction is read stored in IR. After it is stored in IR, instruction needs to be decoded. So needs to be decoded. At the same time, when it's get decoded, some of the other register get populated. That is A, B, and immediate. And next we have executed. So for execution, it is required to get data from A, B, or from an immediate. So for this purpose, we use a MUX. And using MUX, we are select any one value of the two, which is a fed to the ALU, and from ALU we are going to ALU out. So now once data is available in ALU out, it is a sum required to get data from a memory. So that case it hits again the data memory. So it hits again the data memory, and the data is read, then is stored in a register known as a LMD. So after the data getting in data memory and data is read stored in a LMD, finally from LMD we is a final from LMD it is a return to the register bank. It is a return to the register bank in the write back steps. So all these steps that have seen in the bits and pieces from overall slides. So this is a overall diagram for a MIPS 32 designing. So this is a overall diagram for a design of data path of MIPS 32. So conclusion. So the MIPS 32 data part is a complex but well-designed architecture, and that enables the efficient instruction processing. By understanding each stage and how they interact, we can appreciate the intricate working of a modern CPU.